All right, thanks for the introduction and thank Michael for inviting me for the talk. My name is Fan Yao. The title of my talk is Understanding and Enhancing Microarchitecture Security in the Era of AI and Emerging Hardware. So let me first give a brief introduction about myself. So I'm assistant professor in the Department of ECE, and I joined in 2018. I get my PhD degree in computer engineering from George Washington University. And I'm currently leading the computer architecture and systems research lab. The major research focus currently involves computer architecture, microarchitecture security in the form of study covert channel attacks and defenses, and system and hardware security with a recent focus on hardware security for machine learning systems. So as we all know that hardware is the new battlefield for security. So why specifically this is the case? On one hand, performance has been the only focus goal for hardware security over the past few decades. But on the other hand, security processor and hardware is mostly ignored. And it turns out that there are many hardware vulnerabilities in existing CPU and hardware processors. This is especially the case since 2018 with the breakout of the Spectre attack that actually affects billions of computer chips off the shelf. And the discovery of Spectre and the meltdown attack actually opens the Pandora's box. After that, there are many new variants of hardware attack that actually has been shown to be able to severely compromise the confidentiality and the integrity of computer systems. Which actually raise a big concern for this computer security community. Right? In fact, to quote from the Turing Award lecture in ISCA 2018, we've made tremendous gains in IT in the past 40 years. But if security is a war, we're losing it. So now it's really time for computer architects to systematically evaluate the security damage and find out efficient ways to address those problems. So under this context, I'm going to actually briefly introduce a few projects ongoing about microarchitecture security, which are driven by emerging devices and the new computer paradigm of machine learning. So the first project is side channel covert channel attack and defenses in modern and emerging computer systems. So a side and covert channel in general is a form of information leakage attack where you have two processes that try to actually build a stealthy communication channel between each other. And this kind of communication is by default disallowed by the system as the OS, but somehow these two processes can still build the actual communication by modulating the status of the hardware, which actually are shared between them, right? This communication could either be a way where you have this Trojan and spy process that are both malicious and they try to cooperatively communicate secrets, or you have a spy who are malicious who wants to exfiltrate secrets from a benign victim process. So static covert channels are actually extremely dangerous because they can break the isolation guarantee in software, right? Even though from OS perspective, they are perfectly isolated from address space perspective, but they can still build communication between them. And they also leave low physical traces for forensics because as long after this communication is gone, it has finished, there's no status actually could be inspected. And also it threatens the remote computation security, especially for the cloud computing paradigm, because usually in these platforms, we allow multi-tenancy in terms of executions. So this side channel actually brings a big concern for industry, and we see that there are efforts from major chip vendor and the semiconductor companies who wants to actually address them, including, let's say, Intel's confidential computing architecture and ARM CCA. So our objective under this direction is trying to actually unveil unknown or novel side channel vulnerability in modern processors and also in emerging systems. So specifically we have our work has actually identified new variants of Spectre attack on commercial off-the-shelf CPU hardware. So, one example we can demonstrate here is that recent work actually we showed it's possible to build a speculation attack by abusing the status updates of branch predictors. If you can see here, we basically find out that when you execute instructions in CPU, in modern CPUs, even if that instruction is executed and resolved, it will actually update the status of branch predictor. And even though later that instruction execution will be squashed, the status update still can actually remain, not actually restored. So this actually makes an attacker it's possible for an attacker to observe the secrets from victim process by just probing the status of changes from the branch predictor to infer arbitrary secrets from the victim process, which is really dangerous. And we think it's actually more dangerous than the classical Spectre attack because it allows even easier, cold gadget to be exploited. And we can show that by observing the latency differences for branch executions, due to the changes made by the victim process execution, we clearly see that different secrets map to different latency values that could be observed in terms of execution timing. So we further actually propose defense mechanisms, right? The idea for the defense, we call this B-Light. The idea is actually to try to make the branch speculation non-inferable, right? What we do is that we actually augment the classical branch predictor design by giving with a shadow buffer structure that basically stores the temporary unsafe updates of branch predictions. And we only allow the execution of branches in the same domain to benefit from this state update while we will disband any kind of inference from a different domain. So in this way, we actually can ensure the performance guarantee gains by having the state update, but also defeat identified speculation attack that we have actually discovered before. And this design is actually quite lightweight and only has less than 1% runtime overhead for programs execution for representative CPU benchmarks. So besides that, we also want to look at emerging technology, emerging devices, whether they are security issues. And we have focused on this on actually the non-volatile memory, which is in the case of phase change memory or PCM. So NVM or non-volatile memory is a promising replacement for today's DRAM technology because it offers high energy efficiency, high capacity, and non-volatility for the data. But as similar for any new devices you want to put into architecture of the computer, we need to have architectural support to actually integrate them, right? This includes architectural support for read-write techniques, well-leveling techniques, and so on. And there are numerous academic proposals and patented techniques proposed to actually integrate this to support these new devices. But the question we have to actually ask is, are they secure, right? So the lesson we take from Spectre attack is that optimizations for performance optimizations without considering security is a recipe for security problems. So we suspecting actually study the state of the art, read techniques for this phase change memory as main memory, and we identify there is a key security vulnerability that actually enables side channels. Is specific at a high level. This vulnerability allows an attacker to, by observing the timings of executing certain memory traces to the phase change memory, and correlate the timings with certain secrets in victim process, it's possible to actually identify secret values from victim, right? And our existing work ongoing actually also shows that we can actually do a complete recovery of AES keys if a secret program is actually working on AES encryption in the system. Right. As a quick summary, so basically our line of work in this under this domain basically identifies unique and new forms of Spectre attack. And we also shows designs of low cost and effective architecture protection mechanisms, as well as the first demonstration of side channels in emerging devices, which motivates actually we need to have a secure pipe design mechanism in future techniques, a lot by actually trying to identify a problem in a new design and trying to solve this as arm race manner. So this work is actually currently supported by active NSF grants. We have many, leading publication leading values, and we also have security reports actually filed to semiconductor companies to discuss potential countermeasures to this. So with that, I'm going to talk about the second project, which is understanding and investigating trustworthy hardware for machine learning systems. So we know that, okay, now that existing, we have a lot of hardware security issues that we already discovered. And machine learning application is actually quite critical. And security of machine learning is extremely important because it has been applied into many critical systems, security critical systems. So classically, when people look at security of machine learning, they mostly study the external threats, where you have an adversary that try to, let's say, manipulate the input and output to really try to either especially secrets or temper the integrity of the system. But ultimately, we know that a machine learning system will be running on hardware. And hardware is imperfect in terms of security. As we know, there's a host of possible hardware attacks that could happen that either, tamper the system or try to actually steal secrets from the system. The question we want to ask under this, in this project is what are the security impacts and implications of hardware-based threats to machine learning systems? So we actually look at two aspects of machine learning attacks from hardware perspective. The first one is hardware-based machine learning model tampering attack, where, specifically looking at the row hammer vulnerability, which is a form of a common existing vulnerability in state-of-art DRAM devices, where if we flip bits in we can actually flip bits in memory without accessing them, right? This essentially is because of how the DRAM is organized, where if you frequently charge to access the data, you frequently charge one of the rows of a DRAM cells, it actually creates sufficient amount of disturbance to neighboring cells because of crosstalk effects, which may make some of the DRAM cells in the neighboring, actually leak the charge faster, and eventually leads to bit flip. And because your neighboring cells actually can store data belonging to a different application, such as kernels of the OS or a machine learning application, this can cause bit flip or fault injection to the memory of another victim process. So, in common sense, as people, we usually will actually think that machine learning models are actually quite robust. This is especially the case for a state-of-art, let's say, deep neural network that has, let's say, millions of parameters. But our study actually shows that if we combine this attack, this fault injection technique with some kind of smart algorithm to identify the most vulnerable vulnerable ways in the model to flip, then it's possible that we can only use a few bits to fully hijack a modern DRAM models. Our experiments show that only a few, as less than 10 bits, we can actually degrade the accuracy of inference for a well-trained machine learning model from very high level to almost random guess, right? Which shows that surprisingly, machine learning models nowadays are extremely vulnerable to internal tampering. So this research actually opens a new dimension of machine learning called adversarial weight attack, as in contrast to adversarial input attack, which has attracted a lot of attention recently. So second action work that we're doing in this project is hardware-based DRAM model extraction. This is actually very related to what we have done before with row hammer, but essentially we're trying to repurpose row hammer as a side channel attack vector. We figure out that if we put a row hammer with the memory layout where you use the data from the victim's row to hammer the attacker's data, then not only the bit flip is actually depends on the hammer the activations of the rows, it also depends on the data pattern. So it's specifically if specific bits, let's say in the victim, is opposite to the actual the data in the attacker's row, then we have a bit flip after the row hammering. If the secret bit in the victim actually is the same as the attacker's data bit in the targeting cell, then we don't have a bit flip even we do the row hammer. So that's actually, we see that there's a dependency between the data pattern and the bit flip. And this can be used to infer the secret bit, right? Because of the dependency. So actually we see that we can do this bitwise inference with very high accuracy. So with this as a basic attack vector, we use this to actually steal weight speeds of a, let's say, proprietary machine learning models. And this is actually the first side channel that has been shown to be possible to steal model weights, in contrast to model architectures. And with then using this partial exfiltrated weight speed, we can build a local model through substitute model training. And our observations are quite surprising that we can actually extract the real-world DRAM models with very high fidelity, with almost the same level of accuracy as compared to the original model. And also with the knowledge of this local model, we can enable very advanced, adversarial attacks, which basically enhance the augment existing attacks with close to white box attack performance that has only been shown in a theoretical way. So basically, our observation here shows that our work shows the first attempt to understand the effects of model bit flip on DNNs in real systems, which shows that internal adversaries can really tamper the model of machine learning and compromise the integrity in a severe way. And also, we show the first attack that actually demonstrate the way stealing can be practical. And then we really need to consider how hardware attack can really compromise the confidentiality of machine learning model. And our work basically calls for future research in design, secure, and robust architecture for machine learning applications. This actual work is currently supported with inactive NASA projects, and we have publications in top security conferences, and we also have many works actually ongoing in the top venues as well. So the last project I want to talk about is the architecture support for holistic data protection. So based on what I had discussed before, we know that whether it's actually a classical side channel or the attacks on machine learning models, so data is actually the centric for security. But there are multiple attacks that are possible beyond what I have just shown before, right? Including physical attack. I mean, by spoofing attack, they actually can either monitor the data or actually spoof the data when data actually is in transit between the CPUs and the memories. So there are actually existing solutions to try to protect data from a hardware perspective. For example, Intel SCX offers the protection for the memory data by maintaining certain kind of metadata that does encryption and certain kind of integrity checking from the processor so that the data from the memory is secured. But this is actually not sufficient because off-chip you not only have memory, but also you have storage as well. And today's storage devices are very fast and they offer, essentially we can consider this storage device as extension of the memory. So because of this, there's an important need to have a systematic off-chip data protection that actually covers, everything off-chip, not just the memory, right? So under this, because of this, with this motivation, we actually design a mechanism called D-Shield, which is an architecture support for holistic off-chip data protection. So at a high level, what we do is that we augment the processor and integrate a storage security engine inside the processor. So this storage security engine has a purpose of basically check the ongoing I/O transactions between the processor and the storage, and transparently performs encryption and integrity protection using the Merkle tree technology that ensures that load tampering can happen in the storage without being detected by the processor. So this technique actually offers very high performance and also only allows the system to trust the CPU and without any need to change the OS, the kernels, or need support from the storage itself. So how good is D-Shield? And we have evaluations on that shows that it offers very complete data protection with strong guarantees. And it involves only very minimal performance overhead, less than 6% compared to the insecure version that actually is performance. And also has very low cost in terms of design with only 3% storage for metadata and has negligible area overhead. And we actually did implement the logic of this storage security engine with Verilog, and we have synthesized them to evaluate its area overhead and things like that. So so overall, so the impact of this work motivates the secure architecture design for complete data protection, and beyond the data in the memory. And we have actually showed the design of a low-cost architecture scheme with only trusting the processor as root of trust. And this actually can serve as baseline for secure architecture against domain-specific applications in the future, such as machine learning workloads. And this work is published in a top architecture conferences with ongoing papers that are pending in submissions on top values, with also a patent under application as well. So with that, I want to quickly talk about the future research and potential collaborations.
Yeah, if you can briefly cover this, and then we'll get to the Q&A session. Thank you.
Sure. So the short-term research direction involves automated and quantifiable architecture security, where we want to really find automatic ways to identify security vulnerability in microarchitecture. I also want to actually look into composable hardware and microarchitecture security to look into how the defensive schemes from different components can influence each other. In the long-term research direction, I want to look into the security from hardware perspective to large language models, which are actually emerging nowadays. We also want to look into secure architectures for AI accelerators, and the potential collaborations involve come from experts on formal verification, AI and NLP, researchers or software engineering, and the domains of cybersecurity experts. With that, I want to thank our collaborators and our founding agencies and open for questions.